Hello again. I already presented on Tuesday a little bit on performance in parallel computing. Now I'm presenting a little bit more of what I've been working on over the last year and a half or so, because one of basically my pet project is called SpeedyWeather, which is an atmospheric general circulation model, and it's basically supposed to be a playground where a lot of the ideas that Chris has been talking about, we kind of want to stick them in. So we will definitely find some of these ideas of representing certain terms with neural networks. These are all things that are on my to-do list, and not just with an, old school Fortran model, but that's why I wanted to create first a platform where you could actually do this in a hopefully easy way. And so this is why I've been building SpeedyWeather. And SpeedyWeather, therefore, is a little bit different to, let's say, the other models that we've been heard about. For example, Mohit, which has been developed for 1985. So that was definitely before the times of Fortran 90. So it's been a while. This is more a project of me plus a few others, and it's more the timescale of 1 year. But we hope that in the future this will kick off more and more. Because, and this is where I got really frustrated about climate modeling in the past, is that a lot of climate models, especially when they're written in Fortran 90, or even 77, there's some models, I've seen some models written in 77, they are incredibly hard to use, and a lot of the research projects that I've seen that people want to do basically become an entire PhD project, meaning that people have to work on it for 3 years. If instead we could basically come up with an idea and implement it, let's say we come up with an idea on a Monday, implement it on the Tuesday, then we could basically have the results on the Wednesday or Thursday, write a paper on it on the Friday. This is kind of what I would love to be able to do with a climate model. So it should be really that easy. And so as an analogy, and I saw this, I think, on Twitter a couple of years ago, where someone just built a hurricane from Lego, and kind of this is what I would like a climate model to be. So really something where you can almost play as if you play with Lego with it, because if you ask a 5-year-old here, what would a simulation of a hurricane look like without precipitation, that kid would probably just take away the blue stones, and this is exactly what I want a climate model to be. So if you say, I simulate a climate model, I simulate a hurricane, and I can just tweak the precipitation, for example, in it in a super modular way so that it's intuitive and you press play and it still does it. One of the problems that I realized while building SpeedyWeather is that a lot of the current models that we have are written in a way as what we often call a monolithic interface. So they have something like a parameter list. So you compile your model and then you have some kind of parameter list, which is often called a name list or so, where basically all of the parameters you could change go in there. And it basically allows you to do what the developer wants you to do. But if you want to make any more substantial changes, and this is why I've basically drawn this pyramid. So let's say you have your name list and you cannot change the precipitation in the model as you would like to, but the precipitation is actually somehow defined in this green block, which is further down. Then it becomes a PhD project, because the PhD student then suddenly has to say okay, well, I need to somehow branch off from this green block, but then the PhD student need to understand how all of the interaction with the yellow and the blue component, which might be somewhere hidden inside the model, then somehow, how does the information from the name list then propagate down, and so on and so forth, and everything becomes really complicated. And so we thought well, why do we actually do it this way? Why can we not just somehow do it differently? And the solution that we found, and is very much inspired by Oceananigans, Chris just mentioned Klima. Oceananigans is one of the projects that came out of it, and so by talking to the Klima people, the Oceananigans people, I basically also adapted a style, a model constructor interface that I call it, where you basically flip this pyramid on its head. So instead of saying, I have a model and I can run it, you start by building it as if you build it from Lego pieces. And so the model components are basically now sitting at the top. You can basically create these components as you like. And then you pass them all on to a model, and then you say like, here, these are my pieces, I put them into a model, you can initialize the model, and then you can run the model. And so in that sense, we really try to build things up more like from ground up, instead of saying like you have like a single interface where you can go at the top. And so Julia was really amazing for creating these kind of ideas, to play around with kind of ideas of how can you create a climate model, or an atmospheric model in this case, where as few things as possible are hard-coded in. There is still a few things that are hard-coded in, and we deliberately make this choice because sometimes it just gets too complicated if you make everything flexible. But the things that we really care about, for example, that you can play around with different physics inside the model, those ones we didn't want to hard-code. We want to be able to pay people to just exchange them, right? So the green box could be, ideally, be replaced, for example, by a neural network that could then learn something. And so just to talk a little bit more about what is actually happening inside SpeedyWeather. So SpeedyWeather is a spectral model, meaning that you have two ways of representing every field, either in grid point space, what you can see on the right, or in spectral space with the spherical harmonics, what you see on the left. So that is basically, if you haven't heard of spherical harmonics yet, it's basically a Fourier transform on the sphere, and you basically have two wave numbers. Because it's a sphere, it doesn't actually end up being like a square matrix. It actually ends up being this triangle. And so if you choose more of these spectral modes, then you also get a higher resolution in grid point space, but there are some freedoms. And so the way how these spectral models work is that basically you start in spectral space, you transform into grid point space. Some of the computations are done in spectral space, some are done in grid point space, and then you transform back, and then you have the next time step. And that way, you kind of jump back and forth all the time. But you choose whichever operation you have to do on a given time step. You choose whether you do it in spectral or in grid point space, depending on which one is easier. And so often, that basically means you get rid of all of the stencil operations because they're hidden in the transform. So talking about flexibility, SpeedyWeather, and talking about globes and spheres, and maybe also of Earth observations. I don't know exactly what kind of grids you all use, but SpeedyWeather has a grid flexible spectral transform. So meaning these are, for example, 6 of the different grids that we can use. You can technically just define your own and just pass that on. It works. This is exactly how we also defined these. So some of them are quite probably most of the data that you use comes in the one that you see in the bottom left. That's like a regular latitude-longitude grid. But you can also use these reduced grids that basically have then fewer points around the poles. And the grids here that we see on the right, these are heel-pix grids. They are all equal area, so every grid cell has actually exactly the same area, but there might be a bit then deformed so that you can actually cover the entire sphere. And just to show you some examples, SpeedyWeather is actually several models in one. At the moment, we have 2 2D models and 2 3D models implemented, but each of them can obviously have its own individual terms, and you can play around with it. So this is a simulation. I'll just press play here, where this is just the 2D barotropic vorticity model that sits on the sphere. So you basically just have a 2D flow on the sphere, where you stochastically start stirring the flow, and therefore these eddies develop. And we basically just implemented this S term. You can just do it in a notebook. So I'm not going to show exactly how this works, but there's a few rules you have to follow, and then you can basically in the notebook define like, I want to define my stochastic stirring. This is what's supposed to do, and then you just pass that on to the model. That's one example. Another example is another 2D model that we have is the 2D shallow water model, which doesn't have just one equation, but basically 3. So there's 3 variables now, but still 2D. And that one is just where we start with some random waves, and if you press play, these waves start propagating around and basically then start interacting with the orography. And so that's why it kind of looks like water in a pool, because it's essentially, from a physical point of view, it's a very, very similar problem where you just have a 2D atmosphere that's some kind of thickness, and then the waves propagate around. And then to the 3D models, the equations that we solve there are called the primitive equations. So at the moment here, these are just examples. There's also videos in a second, but some examples of like a 3D model then includes humidity, temperature, and also humidity is, for example, removed, which is then precipitation, right? So whenever the humidity gets above a certain threshold, either through condensation or through convection, then basically there's a tendency of reducing the humidity, which is then basically translated into precipitation because it leaves the column and it can evaporate again in the bottom layer by evaporation from the ocean. So that's humidity in there. And then the wind speed is just another perspective of the vorticity that we've seen before. And so, for example, to show, if you initialize the model with temperature, this is currently what it looks like. So you can see some leftovers here from the mountains. So you see that the temperature on top of the mountains is a bit lower. These are some setups that I've been playing around with to understand how the model works, because it's still in development. There's obviously always things that need to be changed. This is another video of precipitation that I've created just recently, and you can see some things work and some things don't, but that's also okay because it doesn't have to be perfect, because I don't want to optimize it by hand, as basically most of the models in the world have been tuned. But we want to do this, we want to automate this and basically just put a neural network in and then basically say like, well, learn whatever's missing here. Because you can see that basically somehow the Pacific, it doesn't really rain in the Pacific, but it somehow rains in the Sahara, which is obviously not what you would expect. But that's also okay because it rains, and the rest is basically something that we want to correct in a more automatic manner. And so just to give you a little, I need to make this bigger again. Oh no, I have also this, what was it again? View, Zen mode. Yes, here we go. But I might want to just, how do I, clear output of all cells. Yes, here we go. So the way how you use SpeedyWeather is, of course, using SpeedyWeather. Let me make this a bit bigger. And the very first thing that you always define in SpeedyWeather is the spectral grid object, which is basically the reason because the defining how you discretize your sphere determines a lot about what is the size of all the different arrays that you need to allocate. And so exactly the logic behind it is basically the first thing that you do if you want to do a simulation is like you want to define where you want to simulate something. In our case, this is always the sphere because of the spherical harmonics. And so here in this case, we define a grid on the sphere in terms of its spectral space as well as the grid point space because of the spectrum model. And so, for example, the 63 now means that this like triangle of spherical harmonics has 63 columns as well as 63 rows. And then we have like one of these grids that sits on top that has around about here a resolution of 200 kilometers, and we use just one vertical level to, for example, have it then in 2D. But there's not more that you have to define. And then you start, and this is exactly where we flip the pyramid on its head, then you start defining all the components that you want to be somehow different to the default. And so just to show, for example, we want the initial conditions to be some random vorticity, but we want to create the planet that we want to simulate on is that we create just like a planet that's like Earth, but with a rotation being equal to 0. And so you see that you could technically, and this is where the whole thing becomes really flexible. We could just define your own new planet. You could define Mars and then say whatever Mars is supposed to have in terms of like rotation, gravity, blah, 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 all of these kind of things. And then you could just basically say like, my planet is equal to Mars. And then it would basically do the whole simulation on Mars. And then this is the magic step is where you basically throw in all of these components that you want to have that are not supposed to be the default. You just throw them in this case, it's the barotropic model, because it's the 2D model that we've just done. Easy one to understand. And then you see that basically the planet will then be used, the initial conditions as we defined will be used, and then you've created your model, and these are now all the different components, all the different colorful blocks that I've shown earlier. And there will be things like we could have defined a forcing, a drag, all of these different terms. There will be things like an output writer, some feedback, all of this kind of stuff. But at the moment, all the components, so really constructing a model really just means that you kind of just like pull all the pieces together, you just gather them. And then the next thing that you have to do, and this is where I love it with Julia. Because of the just-in-time compilation, you basically flip completely around of how you would do it in Fortran, where in Fortran you would first need to compile the whole thing, and then you can basically pass on your parameters. And here, the step of the actual compilation isn't actually done yet, but the initialize already allows things to communicate. So like basically the initialize function calls the initialize function for all of these different components, which for example allows if the forcing, let's say, depends on the gravity, but the gravity is actually, guess what, is a parameter of the planet that you're simulating, it could basically communicate that across. And so this is where then the simulation, the model is initialized and it gives you a simulation object. So this simulation object really contains everything that is in this model, all of its parameter, everything that you have to pre-compute it, blah, 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 including all the variables. Some of them, we call them prognostic variables because these are the ones that really define the model state and define how the model goes from one state to the next. And then the diagnostic variables are the ones that are kind of like diagnosed from the prognostic variables. So they're kind of all the intermediate auxiliary variables that you need to pre-compute in order to know how to get to the next step. And then really the last thing that you do is you just run your simulation and bing, that just ran here in my notebook. At the moment we still have this funky Unicode plot that just gives you a little idea of what actually has been happening. You can obviously just turn the output on and then actually look at it in terms of netcdf files. But I found it super useful as like an interactive tool to understand what's happening. Oh yeah, does it look physical? Okay, good enough for now. And this is where like we use these Unicode plots to understand what's happening. So if you wanted to run it again, I would just press enter again and I would see like, oh, I've simulated another 10 days at a given speed here of about, well, 2,400 days per day because, well, guess what? The simulation isn't super high. So let's do something a bit more exciting. Let's do, for example, and this is where we now define our spectral grid, not just with one level, but actually with 8 levels. So now we basically discretize the entire sphere into 8 different layers. So we're now in 3D world. But I reduced the horizontal resolution a little bit just to be able to run this on my laptop here while I'm basically presenting. And we would construct the model as before, but because now we're doing this primitive wet model, so that's a primitive equation model that also includes humidity. So you could also do it without humidity. You could basically think of a dry atmosphere. And now suddenly we have a model that has way more components. So you see here there's things like, there's an ocean model, there's like orography, there's a land sea mass, there's things like condensation, there's some thermodynamics in it, evaporation. And you could basically, in the same way as before, you could just basically define them as you want and just throw them in. And this is how you define your new model, and then you do the same thing as before. You initialize that simulation. And the cool thing is, and this is what I really love about doing these kind of simulations in Julia, is that at any point in time you can interact with all of your objects, meaning that I could also just, like, before I even run the model or after I run the model or in between, I can just investigate what's happening. And so here, for example, I'm just plotting the land sea mass that's currently part of the model, but I could also plot anything else that's inside the model, and you get a rough idea of, this is roughly the resolution that we're going to simulate in a second. So you see the continents look a bit pixelated, but that's fine for now because it's just in my laptop here and it should be quick. But you could also, and this is what I found super useful with Julia, is that because there's obviously a lot of computations happening inside such an atmospheric model. There's a lot of functionality that we need to use anyway. But the way how we've written this is that we basically expose all of this functionality directly to the user. So instead of saying, like, I don't know, I can compute my gradient somewhere down in the bottom of my model, then you get the output, and then you give the output to a PhD student, and the PhD student has to figure out again how to do the gradient. No. We do this differently. We basically try to expose all of the functionality directly. So if I call the spectral function here, it's exactly the spectral function that's also inside the model, transforming just from this grid point space that you can see here into spectral space. And if I then plot this, you could see this is what the land sea mask would look like in spectral space. And here's basically, you can just about see that there's some power in these like lower order modes, but this is basically exactly your triangle of the spherical harmonic. So you could basically just do the spectral analysis here. You could look at the spectral power. You could do any kind of other analysis that we have here. You could interpolate between different grids, because guess what? We have these operators anyway in the model, and so you should also be able to use them. And so if I run this model now, I'm not quite sure whether I compiled this yet, so it's probably just currently just in time compiling it, so it might take a few seconds. Let's wait for that. And here you can see I just like put the output to true, so that we can hopefully look at the netcdf file in a second and see what happened there. Yeah, exactly. So now it's simulating. You see it's definitely much slower than it was before, because guess what? We also have a third dimension now that we're simulating. And it will give us in a second basically a little bit back of what's just been simulated. That obviously doesn't tell us necessarily, like, I'm used to these plots, so I'm kind of, it tells me a little bit, but we're definitely thinking about something a bit more, like some kind of small feedback that you get directly after the simulation so that you know what happened. But often what I then do, and let me escape this here, is that, let me get a new terminal here. I think we were in talks, JuliaEO, no, where are we? 2024. And then what we just simulated was this one here. And so this is this NC-Vis viewer. I think it's a bit similar to what Francesco displayed yesterday for HDF5. And now we could, for example, look at humidity. This is now at the top of the atmosphere. So let's go maybe a bit further down. There's more humidity the further down you go. So let's say this is, I think, surface humidity. And now you could just press play and see, maybe let's give it another color map that looks a bit more like humidity. And so you can see how humidity is concentrated in the tropics and how this is moving around. You could then look at, and this is basically how I developed this model a lot, that I just look at, oh, what's happening here, what's simulating, that looks reasonable, that doesn't look reasonable, or there's something going on. This is, for example, vorticity at the lower levels, but you could also go higher up, and you can see how this simulation was working out. And basically, my dream for the future is to have a model that is as easy to use as this one, but that really can also do really high quality research by, for example, just putting like a neural network in, let it learn something, and be able to, it should basically be, and this is really, I think, where this is trying to get at, it should be as easy to use for, like, say, an undergrad or master student as it is for someone who does research. And if it's really easy to use, I also hope that it will really accelerate the research that we do, because if it's already hard for someone with a postdoc, with a PhD to do this kind of stuff, then guess what? You're not going to be the fastest at something if you can do it as an undergrad or as a master student. Thank you. Any questions? We can run it again if you want to.
Milan, thank you very much. What about the ocean?
Yeah, so
do you have
SpeedyWeather at the moment has this, it's basically just prescribed SSTs at the moment. We have created, because we just thought like it would be nice to have it a bit more flexible. So it is a general interface where basically on every time step, it's just the ocean is just called, and at the moment the ocean model is a seasonal climatology model. So that basically just pulls a seasonal climatology from data and just steps forward in that sense. There are obviously like ideas to couple that to a real ocean model. It's definitely something that's on my to-do list, but it's not something that's super easy. Like, it's not something you do in a day. And so, yeah, I don't really know exactly where the whole coupling is going to go in the next years. Because I think there's already a lot on the to-do list if you think about putting neural networks in and let it learn something. And so I don't necessarily always, with this model, I don't necessarily want to go down the conventional way of model development. I deliberately want to skip some of the things that large teams have basically spent decades on solving for the individual models, that I feel like if I would do the same, I would still give the same talk in 20 years and wouldn't really give you necessarily an update. And I kind of want to try to go into very different directions and like basically use this as a starting point, but now go into like try to do things differently and see whether they actually bring you faster somewhere where this is something useful than the conventional modeling approaches are.
Okay. Thank you. Yeah, I also agree you should go different.
Thank you very much for your presentation. Just one comment. Have you done some comparison with traditional models with, I mean, very simplified implementations? Do they behave similarly or in a different way? Like, I don't know, like the WRF or something like this?
So if I got your question correctly, like, no, sorry, say it again. What was your question?
So what I mean is that you developed this from scratch,
yeah.
No? But there are already existing models that they are doing with the probably programming in other language and develop with longer periods like WRF.
Yes, WRF. Yeah.
Have you done any comparison try to run them in a simplified manner like the one that you saw here to see if they match, they don't match, what are the differences?
Yeah. So that is definitely something that at some point needs to be done. At the moment, I've been implementing a couple of these like test cases. They're like baroclinic instability test cases to see that the model is actually simulating the right thing. It does on those ones qualitatively, but I also don't want to like I don't know, spend a year on just like exactly like doing like a quantitative analysis compared to something else, because in the end I actually would like to go away from other existing models and directly want to reference it to data, so that you could, for example, say like I just press play here. I could run it for 100 years if I wanted to, and I would get, for example, some kind of climatology for, let's say, temperature over the Azores, and then would directly reference it to that data. And then ideally, you could, in the similar way as like Chris described today, where you just basically plug in a neural network as like a correction term that takes care of everything that you don't know, that should obviously then learn directly from this data. And so, yes, of course, at some point we will like compare to other models, but I don't think this is at the moment the main focus of this work. Yeah. Great.